Thank you everyone for joining today. My name is Nathan Piccini. I am a marketing manager at Data Science Dojo, and we're really excited to have Daniel here with us today. Daniel is the head of data at Clip down in Mexico, and also the author of Analytic Skills for AI and Data Science, which was published by O'Reilly back in 2020. And today he's going to be presenting translating data into effective decisions, and we're just really excited to have him. So Daniel, why don't you go ahead and take it away?
Great, thanks Nathan for the intro, and hello everyone. I'm super happy to be here with such a diverse crowd. I'm hoping to have a highly interactive session. So as Nathan said, please share your questions in the Q&A section tab. Okay, great. So I'm going to start now. So the title of the talk is how is translating data into effective decisions. But let me tell you a bit more about what we're going to cover, and hopefully that title will be way more clear in a couple of slides. So I'm going to start telling you how I got here and thinking about translating data into effective decisions. Then I'm going to basically claim that what we learn as data scientists lacks part of this knowledge. It's kind of understood that we learn it on the job, and that the problem with that approach is that it can take us several years until we're really productive and creating value for the companies. Then I'm going to try to convince you that this is important for data scientists, that decision making is quite important for data scientists. I'm going to go and tell you exactly, I'm going to give you a simple decomposition of how decision making can be thought or decomposed into different sections that will help us a lot, really understanding where our toolkits from data science come into the play. And finally, I'm going to make some remarks on okay, we learn a lot of machine learning. How can we use that for decision making? Great. I'm going to be stopping at the end of each section to see if I can answer some of the questions on the Q&A tab. Great. Just before we start, and to align and set up expectations, this is not a talk about soft skills. I'm absolutely convinced that soft skills are critical for us to be able to make effective decisions. And I'm absolutely convinced that it's probably the most important determinant of our careers. But I'm not going to talk about that. I'm going to talk on the harder stuff, the more technical stuff. And the talk won't be that technical. I'll try to leave it to a very high level, but hopefully you'll see I'll be able to convince you that underneath some of the things that I comment, there are some really hard technical stuff that are quite cool to learn. Okay, so let me tell you very quickly how I got here. So my background is in economics. I got a PhD in economics, very quantitative, lots of coding. So the transition to data science was relatively easy. I really loved, and to this day, I really love coding and solving problems. So as many of you or most of you, that's what I really loved at the beginning of my career. And I did a lot of things, a lot of machine learning applications, very, very cool stuff for me at that point of my career. After several years, I got my first leading role or manager's role. And then I really understood that we as data scientists are quite constrained in how much value we can create. And there's a problem in the conversation with our stakeholders. Stakeholders have different expectations of what we do. So we're always evangelizing about the data-driven approach. But still, I thought that I lacked like a framework to really think clearly about how to do this. And I decided to write down some of my ideas, and it ended up in a book. And that's what I'm going to show you here is exactly how I lead the teams that I now lead. And it's my philosophy towards data science. Cool. So let's start with the basics. So what do we do as data scientists? So here on the right, I got a screenshot of a very typical data science curriculum that I found online. And the important thing is here in the section of acquired skills, you'll see that they're really focused on methods: research, design, data engineering, machine learning, mining, visualization, ethics, statistical analysis, and some communication. So we are being trained to become experts in methods. That's the core of the data science training that we mostly find out there in the market. And if you ask the question of why is that the case, at least my partial answer is there are way too many things to learn in such a short time. It can take years for us to really become experts in all of these techniques. And indeed, in that short time that we have to become data scientists, we're really trying to maximize the probability of success for us at that point in our careers. And success for us is getting hired as data scientists. And companies are looking for experts in the methods. So there's like a match of skills here. Companies want that, so the training goes there. The problem-ish that I find here is that really algorithms, all of the algorithms that we learn, all of the techniques, all of the methods are not necessary, are necessary but not sufficient if we change the objective function. Once we are hired, really successful data scientists should be creating value for the companies that are hiring us. So let me try to redefine success, and I'll start with a quote from a leader that I met some years ago, data science director in a tech company. That person basically said, the best data scientists are those that are able to influence the decisions or the decision-making process within a company. And at that time, I thought that made sense. But I think that we are self-constraining ourselves, and probably you are all encountering this at your jobs if you're currently working, or you will encounter it if you're finishing your training right now. We tend to think of ourselves as those persons that provide inputs for someone else in the company to make the decisions. My approach to data science is that we should be helping directly to improve the decision-making process at the companies. And we can do that with our data science toolkit. We can do it in a scientific way. That's the whole purpose of this talk. I'm going to try to show you the scientific approach to that effective decision-making through data science. So let me give you, of course, my definition of data science. And this is very similar to the definitions that you'll find elsewhere. And I'm sure that you maybe like other definitions better than this, but let me give it a try here. So I think data science is scalable, systematic, and replicable, evidence-based business making. So I divided that sentence into 3 sections. The first section is all about the methods, scalable, systematic, and replicable. In the past 20 or so years, there has been a revolution, a technical revolution, both in algorithms and compute, that allows us to do that right now. The second part has to do with the scientific method. And I think we forget that we as data scientists are scientists. We ought to be scientists. And that's the evidence-based part, what some people call being data-driven. And finally, but it shouldn't be the last part, we're in the business of improving the state of our companies. We should always focus and we should always start with improving the business. So the first section is what most curricula out there present in a systematic way. We learn many methods. The second part, the scientific method, I don't think it's super highlighted in the curricula, but most likely it has some part. And the final part, we really learn on the job. And I think that's normal. We really need to learn our business to be able to improve the business. Okay, so why care about decision making? So my main claim and my main approach towards data science is that value of companies is created by making decisions. And I've had conversations about this statement with many people, and some people argue that that's not always true, that just creating knowledge, improving the knowledge base of the company creates value. And I kind of think that that's true. We learn things and we accumulate that in the knowledge base. But if we care about quantifiable value, and that's why they hire us as data scientists, then knowledge is not enough. We really have to try to improve the decision-making process, because value is created by making decisions, and I will be providing many, well, not that many examples in later slides. So if that's the case, if this claim is true, that companies create value by making decisions, and since I, as a data scientist, want to create quantifiable value, it kind of follows logically that I should be trying to improve the company's decision-making capabilities. And since I'm a data scientist and I love what I do and I know my methods, I'm going to try to do it with my toolkit, possibly enlarging the toolkit, as I will also claim later in the talk. So now let's go to the types of analysis or work that we do as data scientists. This some people call this value creation or transformation evolution or stages. So let's talk about at least the most basic types of analysis that we can do with data. Of course, there's the descriptive stage, the predictive stage, and the prescriptive stage. Most machine learning focus on the predictive part. The descriptive part has, if you look at what the market, what data science, the data scientists and data analysts do, the descriptive stage, it's either in dashboards and reports, and we kind of tend to think of that as business intelligence. But data scientists that are working on predictive models always start with a descriptive analysis of the data, some exploratory data analysis, some EDA. So descriptive is always at the beginning of the process. Then, if we think we have a good understanding of the problem, we can try to predict some outcomes that are relevant for our companies using machine learning. And finally, we can actually try to prescribe the best action plans for the company to improve our business. And if you see here, there's an implicit, actually quite explicit claim that these stages are ordered in terms of the value, the quantifiable value that you can create with each of these. So on the descriptive side, I claim that the value is quite low, essentially because we're looking at the past of the company. And we can learn many things and we can find patterns in the data that tells us interesting things about the past. It's hard to make decisions with the past to create quantifiable value. And I will repeat many times quantifiable because for me, we as data scientists have to be able to show the impact of our teams or of our work in terms of the relevant measures that the companies have. So it really has to be quantified. The predictive stage, I claim, may create some more value. It may or may not. I'm not sure if in your experiences, but in my experience, I've built many predictive models that really created no quantifiable value. I will give you an example later also of one such predictive model. And finally, and I think that's the easiest claim to believe, is that the prescriptive value creates a lot of value. The prescriptive stage creates a lot of value, I'm sorry. Why is that? Because by definition, the prescriptive stage is about finding the best, it's about optimizing the best action plans or decisions for the company, given a predefined metric. So just by definition, we're looking for the most value. The prescriptive stage is about finding the highest value that we can. So it has to create more value than the other two. The other two may be completely flat. Sometimes the descriptive stage may actually provide more value than the predictive stage, but I think we wouldn't argue about the fact that just by definition, the prescriptive stage ought to create the most value. And the prescriptive stage it's all about decision-making, because again, the prescriptive stage is about prescribing or recommending the best actions or the best decisions that we can take for the company. So let me see, I think I now have a question here. I will be certainly, yes, Andrea, I will be certainly talking about causal inference later on. It is absolutely critical for the prescriptive stage. I hope I answered your question. I think there's something, okay. Please, I see some comments on the chat. I'm not looking at them, so if these are questions, please just type them on the Q&A tab. Thank you. Okay, great. So let's try to understand what decision-making looks like, and then we'll be able to find some clues on how our toolkit can help us creating value through better decision-making. Okay, so let's focus on the diagram on the right. So every decision has at least these four main components. First, we care about the results. We're making a decision because we care about the outcome of the decision. So I'm starting on the left, on the right, I'm sorry, and then I'm going to be moving to the left. So we always care about some predefined KPI or metric that we want to impact. The next point is, okay, we know that we want to impact these KPIs. What can we really do about those? How can we impact those results, those outcomes? That's where the actions or levers come in play. The problem is that the actions, not necessarily, and it's almost always the case, at least in a business setting, that actions don't directly affect the results. And the typical example is, yes, I want to improve the revenues or the profits of my company, but I cannot force my customers to buy our products or services. So we actually have to create some consequences that are directly caused by the actions by the levers that we pull, by the actions that we make. So there's a causal link, going back to Andrea's question, there's a causal link between actions and consequences, and the consequences themselves impact the results. And finally, in most interesting, and I would argue in all decisions, but let me not be dramatic about it, in most interesting decision settings, there is underlying uncertainty. And what that means is that if I decide to pull this lever or take this first action, several things can happen. It can be that this consequence arises or this consequence arises and so on. And we are not really sure, we're not completely certain which consequence will arise. So that's what I call the underlying uncertainty. Let me go one by one onto this, and I will try to tell you where the data science toolkit comes in play. So let's start with the results. We should always start with the business. We should always start with the result, with the metric, with the KPI, with the outcome that we want to impact. And of course, if that's the case, that we should always start with the KPIs, it must be true that we need to choose the right metric for the problem at hand. And there's a lot of literature on this. I won't enter into the literature. For me, good metrics should have three properties. They should be relevant, they should be measurable, and they should be actionable. So what does relevance means? We should always ask the question, is this the right metric for the decision problem or that we have at hand? Almost always, it's not. Almost always, you have to dig in deeper and look for a better metric. And I will show you a couple of tricks for doing that in the next couple of slides. Second, of course, it has to be measurable. I have to be able to quantify the impact, because otherwise there's no way to tell whether the decision was effective or not. And why do I say that? Probably you're thinking that all metrics are by definition measurable. It's kind of true. Metrics are measurable. The word means exactly the same thing. But there are some metrics that are easier to measure and other metrics that are harder to measure. Example of an easy metric is sales. Hopefully at our companies, we all know how much we sold in a given period. So that should be easy. But a little bit less easy or harder to measure, customer satisfaction. So how can we really measure in an objective way customer satisfaction? So there are metrics out there. There's the Net Promoter Score or NPS and similar metrics that we go and ask our customers, rate us. And we use that rating as a measure of customer satisfaction. And sometimes it's a good measure and other times it's not a good measure. And the reason why sometimes it's a good measure and sometimes it's not a good measure is because we are asking our customers to tell us what they think. Most of our customers will not answer the survey. And those who did self-selected themselves into answering the survey. And it's almost always the case that the haters of the product will be quite likely to answer the survey. And the lovers are not really that likely to tell us what they think about our product. So basically what I'm saying here is that even if we think that we can measure something, that metric can be biased. The NPS, the Net Promoter Score, may not be an unbiased measurement, may not provide an unbiased measurement of customer satisfaction. So measurability is critical. We take it for granted, but please don't take it for granted. And finally, it has to be actionable. Is it really actionable? Can we impact the metric directly, or does it depend on some intervening phases or customers? So these for me are the three critical metrics, and that's where I always start. Start with the metric and see whether it's relevant, measurable, and actionable. Okay, so relevance and actionable. These two properties, if we take for granted measurability, then the two other ones that are quite important are relevance and actionable. Many times we start with a metric, and that's not really either measurable, relevant or actionable. So we have to start looking for better metrics. So I'm gonna show you in the next few slides a trick that I use, if not on a daily basis. There's not a week where I don't use this trick or someone in my team. So let's start with revenues. We as data scientists work for a company, and companies grow if revenues are increasing in time. So it's kind of a reflex for us to start thinking, okay, let's do this. Let's make this decision to impact revenues. That's absolutely natural. We always start with the top line metric that we know that will have a lot of visibility in the company. My claim, at least in my experience, that's not always the best place to start. We should try to decompose revenues into something that's more actionable and at the same time relevant for the problems that we're solving. So I'm going to give you here on the next couple of slides, I'm going to continue with the example of revenues. So revenues can be first decomposed into the price that we charge and the quantity that we sell, the sales. So revenues, we started with one metric and we decomposed it into two metrics. The nice thing about prices is that companies choose the price. Maybe if you're in a regulated company sector, maybe you don't have that much space to move the prices. It's certainly actionable. We as companies are able to decide what price we're going to charge for what we sell. The second metric, the sales, are not directly actionable. This is chosen by our customers. So while this is a good metric, this is not the great metric. So let's go to the next slide and see how the trick works. So I'm going to start decomposing revenues by using the following trick. Each time I will be multiplying and dividing by exactly the same metric or quantity. So the equality is always maintained. I'm always multiplying by one. So I'm going to start here on the left. I started with revenues. I added a time subscript that will make sense in the third line. But for now, I start with revenues in time t. And the first trick is multiply and divide by the sales, by the quantity sold. So the equality is maintained. I haven't done anything to the revenues. The interesting thing is just by multiplying and dividing by the quantity sold, I get the average price here. So this fraction here is actually the average price. So that's how I got the previous equation. Revenues is equal to the average price times the sales that we have. That's the trick used for the first time. Let's continue. What about multiplying and dividing by monthly active users? So I multiply and divide by monthly active users. And instead of two metrics, submetrics, I now get three submetrics. The price that I got from the first equation, the monthly active users, and now I have the sales per user. So these are three submetrics that I can try to see whether they're actionable and relevant. And I can go even further and decompose monthly active users using a flow equation. That's always true, that the monthly active users in period T have to be equal to the monthly active users that I had in the previous period, plus the new users that we had in this period, minus those who churned. And also here, the sales per user. So notice how I started with the top line metric that I had, revenues, and I used twice the trick of multiplying and dividing by a relevant metric. That's the hard part about becoming experts at the technique. You really have to learn to understand what's the relevant metric to multiply and divide by. So I started with one metric, revenues, and I ended up with 1, 2, 3, and 4 submetrics that are now more actionable and or more relevant. And I can actually continue this. You can actually decompose new users using the same tricks, and change users, not exactly the same tricks, but you can take this a couple of levels further to find the right metric for your problem. Okay, that's the trick in action. Let me show you another example of the trick in action, because I really think that we should all learn about this trick. Funnel analytics. I'm sure that some or most of you have worked with funnels before. So a typical example of a funnel is we want our customers to buy our products, but for that, the first stage is always start by downloading the app. Once they download the app, they have to open it and finish the onboarding stage, and then finally buy the items. I'm simplifying the funnel. Usually you have more stages here. Let's have only 3 stages here: download, onboarding, and finally sales. So that using the exact same trick as before, let's decompose this funnel. And the trick for funnels work as follows. You always start with the outcome that you want to optimize, that you care about, sales here, and then we move leftward, just by multiplying and dividing by the metric in each stage. So I have it here. I start on the right hand side, sales. I multiply, so sales is equal to sales. We all know that. I multiply and divide by the number of onboarded customers in a period. So I multiply here and divide, so the equality is maintained. And finally, I multiply and divide by the number of downloads. So you might be wondering, what did we achieve here? I started with the metric that I care about, but it's not directly actionable and actually not really relevant for many problems that we may care about, and ended up with 3 metrics, sub-metrics, that are more actionable and might be more relevant for the specific problem that we're trying to solve. So this ratio of sales to onboarded, I'm just calling it the sales conversion rate. Out of 100 people customers that onboarded, that finished the onboarding process, how many converted into sales? This second term that I have here, I'm calling it the onboarding conversion rate, the same thing. Out of 100 downloads that we have, how many ended up onboarding? And finally, the downloads. What's really interesting about this decomposition, you may not see the richness of this decomposition, is that each of these may have either different levers or actions that we can pull or take to improve them. And even more importantly, on a business setting, different stakeholders. So the owner of this metric might be someone from that team. The owner of this metric might be someone from another team. So let me give you examples of those levers. For instance, we want to improve the sales conversion rate once they onboard it. What are the type of levers that we have here? You can either call your customers or send them an email, or you can pull the pricing lever that's always there. So for this specific submetric, we can actually think of a high number of levers that we can pull to improve. The second metric, the onboarding conversion rate. The typical scenario here is that the UX UI team at your companies are trying to smooth out the funnel, the whole onboarding process, so that they maximize this conversion rate. Out of 100 that start the process, how many end up finishing it successfully? So usually the type of levers that we have here are related to the design of the onboarding process, the design of the app, and so on. And finally, downloads. So we need more traffic into our webpage, or we need more traffic into our app. Usually the typical levers that we have here are related to marketing, either performance marketing, online marketing, or more traditional marketing channels, and so on. So I hope that you get the main point from this slide, from these 2 slides. One simple trick: start with a metric that you really want to impact at the end, and find more directly actionable sub-metrics that we can actually think about hard on how to improve them, finding levers. Okay. Let me stop here because I know that I have a couple of questions. Okay. So Femi, I'm not sure if I'm pronouncing your name correctly, sorry about that. Do you have any thoughts on the trade-off between creating long-term and short-term metrics? Is it even possible to create actionable long-term metrics? That's a great question. Actually, one of the other properties about metrics, so we said that they should be relevant, actionable, and measurable. The measurability part of, so basically, if Femi is asking whether we can create long-term metrics, I think you can, but the problem with longer-term metrics is that it's very hard to measure the impact of the lever on the metric, because many things can be happening in the intervening time or phases. So yes, people use longer term. I really prefer really short-term metrics that I can very simply measure. The second question is from Ali. What platforms or tools would you advise for beginners in data science? Okay, I'll leave. So that question is kind of unrelated. Let me continue to with the talk, and I'm happy if we have time, we can talk about that, Ali. Okay, then we move to the actions or levers part of the anatomy of decision making. So once we define the metrics, the natural question is, how are we going to affect those metrics? And there are some obvious levers that everyone uses at any company. As I mentioned before, pricing, we can always change the price, either increase it or decrease it. Advertising, communication, web design, these examples I think I have already mentioned. So it's kind of standard to always start with the low-hanging fruit. And these are kind of the low-hanging fruit. These are kind of the easy levers that we find. The interesting thing is that some of these levers are either more costly or more effective. So for instance, pricing. Once a company decides to decrease their prices, it's really a big decision. You're signaling to the market that you're lowering your prices. So it can actually be quite costly, a quite costly lever. Most companies try not to use it because of that. Advertising is also costly, but may be effective. Communication is one that I really like to test in the companies that I've worked, because it's one of the cheapest levers that we can pull. But that small price for improving the communication may also imply that they're not as effective as for different problems. Communication may not be really effective. The point here is that there's a plethora, there are many levers that you can think about. Since we're thinking about optimization or finding the best actions, we have to test some of these, and most likely start with the less expensive one and see whether they're also effective. But once you try these low-hanging fruit levers, my advice is try to think out of the box. And there are many ways to do that. It's not easy to think out of the box, but the approach that I usually rely upon is thinking about those cognitive biases that we as customers have, and try to find actions that make use of those cognitive biases. And this is a great book by Dan Ariely, Predictably Irrational. I'm sure that you'll find many, many examples of out-of-the-box levers. Then we move to consequences. So, as I mentioned before, the interesting thing about consequences is that consequences themselves create the results and arise causally from the actions that we take. And as I said before also, they're usually uncertain. The interesting thing about the consequences, and I think that's a big part of the storytelling skills that we as data scientists should develop. And let me emphasize the scientist part of the data scientist role. We should really think hard about hypotheses. We should always start with a hypothesis backlog saying, if I do this, our customers will do that, and that's how the results, the KPIs will be impacted. So that's at the heart of the scientific method, and we should really try hard. And people in my teams are always hear that from me. Tell me the story behind what you're proposing, because otherwise I don't see what we're testing. And here's an example, just to be sure that we all understand what consequences are. So let's go back to the pricing lever. We're considering of reducing our prices, and there are many possible consequences, but I'm simplifying here. There are two possible consequences. Our customers can now buy more of what we have. Notice that this is a decision made by the customers, not by us, and therefore we end up with higher sales. The lever, the consequence is that our customers buy more, and the results higher sales. There's another possibility. Some or most or all of our customers may think that the product is of lower quality now, and we have the exactly opposed outcome, lower sales. So that's why this set of consequences is so important for us, because you may have heard of the phrase unexpected consequences. We tend to think that this is the natural path for a decision, and we generally don't consider the other possibilities. We have to think hard about those other possibilities in advance. Finally, underlying uncertainty. So going back to the previous example, customers can either buy more or buy less because they think the product is of lower quality. And we don't really know which one of these will arise. We may be confident about the first outcome, but we can't be certain. So it's quite useful to think about this in terms of probabilities. There's a probability mu that we will get this outcome, and the remaining probability that we will get the other outcome. That's where underlying uncertainty comes in. And that's where our main toolkit, machine learning, will help us out as data scientists. Data scientists are experts at estimating or training models, and models is all about prediction and tackling uncertainty. So for all of you who use machine learning on a daily basis, my suggestion, or what has been quite useful for me, is to take that toolkit of that prediction toolkit, and map it onto the actual decision that we want to tackle. Okay, I think I have a question here. I think it's the same question. Okay, great. So let's move forward to machine learning and data science in decision making. So whenever you think about data science and decision making, the first thing I think about is A/B testing. A/B testing is the quintessential example of data-driven decision making. And if you have worked with A/B testing, most likely you have thought about bandit problems also. But let's start with A/B testing, because the A/B testing process is quite, at least on paper, is quite easy to understand. How does it usually? What does it take to design an A/B test? We always start with the KPI. We should always start with the KPI that we want to improve. We then move to the levers. Are we changing the communication? Are we changing the size or the color of the button on our website, and so on? We move forward to the hypothesis, the consequences, and build a hypothesis backlog. And finally, we tackle underlying uncertainty. In the context of A/B testing, underlying uncertainty comes in the flavor of size and power calculations. And I have an example here of a typical way I would present the results of an A/B test. So we tried our current option, that's the A option, and we're trying the new lever, the B lever, and then we measure the average impact, the impact on the average KPI or metric that we're measuring. And we see whether there's both statistical power, statistical significance, and statistical power here. We're always looking for A/B tests that are not underpowered. If we find a difference, as we have here, it appears to be that the B lever was superior to the A lever. We really want to be able to conclude that there was an effect, and not that difference is just because of noise, of randomness. So that's where the underlying uncertainty kicks in, and that's part of our toolkit. Very standard A/B testing. But we can do way more than A/B testing. And again, A/B testing, we should be doing a lot of A/B testing in our companies. I love A/B testing. It's a really fast way to iterate and improve decisions. But there are other things we can do with our toolkit. So I started before I was claiming that with these two possible outcomes, you can actually assign a probability measure here. So there's a probability mu that the customers will buy more, and 1 minus mu that the customers will end up buying less. So if we were able to estimate the probabilities with our machine learning toolkit, for instance, classification models, then we would be able to compute the expected revenue given the lower prices. So the expected revenue is just the probability of higher sales plus the remaining probability and the revenue coming from the lower sales. And here the notation might be confusing. P0 is just the lower prices, and cap Q of P0 is just a sales increase. And the same thing here, lowercase q is just the lower sales that we have. So notice that one, if we are able to estimate the probabilities, we are then able to compute the expected value. And the interesting thing about computing expected values is that we can now optimize our decision. There's a very simple decision rule here. We should lower prices if and only if the expected revenue from doing so is at least as large as the revenue that we had with the previous prices. So notice that we moved from a hypothesis, prices affect our revenue, into optimizing a decision. That's the optimal decision that we can make in this setting, in this very simplified setting. What do we need? And for this, we need to be able to estimate the probabilities. As I already mentioned, the standard approach to do that is using classification models, but we also need this function here and this function here. And and this function here is just telling us, given that we lowered our prices, by how much will that increase, or by how much will that decrease? And if you're familiar to the term price elasticity, really what we have to do with our machine learning toolkit is estimate the price elasticity of the demand of our products in our companies. So from our toolkit, we need to do two things: estimate this and estimate this and that. It's not trivial, but we can do it with our toolkit. And we optimize a decision. Okay, let's move to supervised machine learning. The next step. So this type of problems that we encounter all the time. We're given an outcome to predict Y. We go and look for the features that will help us predict that outcome, and the algorithm will help us learn the data generating process of this relationship. It should be quite familiar for all of us who have estimated models, supervised models. That's cool. I've done that many times, but then I go back 2 steps and start with the question, okay, why should we care about this prediction? What can we do with this prediction? In a decision making setting, we cannot really do much about this prediction. We really need to convert this into a decision problem. So let me give you an example that I've done several times in my career. And the typical example is the lever that we want to pull is making an offer for one of our customers to buy something. Send them an email, call them, send them a push notification or so. That's the lever. We want to impact sales. So usually what we data scientists do is, okay, I'm gonna go and train a model that will predict, that will give me the probability that each of our customers will buy this specific product. And we do that, we're great at that. We have a very good prediction model, and we end up with a probability score. So the standard approach to convert this into a decision problem is we start by ordering the scores from highest to lowest. And then we go to our stakeholder and tell them, look, I'm gonna send you the top 5% of our customers ordered in that way, because we think these are the likeliest customers to buy the product. That's the case, and they go and try the campaign and so on. Notice that we converted a prediction problem into a decision problem. There's a decision rule here. If the probability score is higher than some threshold, then we will be making the offer. So prediction by itself is not creating value or changing the decision, but the decision rule that was built upon the prediction, the score, was actually able to deliver the result. Let's move one step further. So what if we expand the set of features in a standard machine learning supervised model? Same thing. We want to predict outcome Y. We have the set of features here, but we now have augmented the set of features, and we included the levers that we actually have. Suppose that I include here the price of the goods that we're selling, or the communication strategy, or the size and color of the buttons. We can actually include the levers on the right-hand side. So in principle, we should be able to estimate this, and that will give us everything that we need. It's super cool, and it would create a lot of value. We can simulate pulling a lever and see the outcome, the predicted outcome given our training data. So in principle, this should work. the point that I would love to make here is that really the current machine learning toolkit isn't, we can certainly do it, and many people do it. Well, I wouldn't say many, but some people actually do this. We, in our team, we actually do some of these things. But the machine learning toolkit is not the best one here because, as Andrea mentioned before, there's a causal link from the levers to the predicted outcome. And machine learning is great at prediction, but it's mostly correlations. Machine learning has very little to this day. Machine learning has very little to say about causal inference. And there's a big branch of people. There's a lot of people in the world working on this because that's really the next frontier of machine learning. There are several frontiers for machine learning. AI is one of those, but really AI without causality is hard to think that can actually exist. And the other thing that I would love to notice is that causal inference is almost always absent from data science curricula. Economists know a lot about causality. Other social scientists also know about this, but the main curricula, the average curricula, don't include causal inference. Causal inference is super hard. It's a different type of class of methods that we should be able to learn if we want to do something like this. If you want to do something like estimate a prediction, given that we pull the lever, we need to move into causal inference. That's why I always say that incrementality is the holy grail of data science. So you might be wondering, what's incrementality? Incrementality is just measuring, being able to quantify the causal impact that our levers have on our results. And notice that if we are able to do that, if we're able to find incremental effects or decremental effects going upwards or downwards, pretty much the decision problem is relatively easy or trivial. If we know the impacts of two levers, we just take and continue using the one with the higher impact. So local optimization is super trivial, and that's actually what we do with A/B testing. Small change, improvement, stick to that. Small change, improvement, stick to that. That's what I'm calling here local optimization. And we should always start there. But we can kind of move to what I'm saying, calling here global-ish optimization. And the ish is very important because I don't really think that we're able to tackle global optimization in the most expanded way to understand it. So it's global-ish in the sense that if we're able to figure out to model the entire problem, making simplifying assumptions, that's one of the things that we need to learn, one of the skills that we need to learn. We have to make some simplifying assumptions. Then you can actually attempt something like global-ish optimization. And that's why incrementality is the holy grail for me for data science. If we're able to measure this, at least we can do local optimization. Great. So I have a couple of questions before thanking everyone. How do you estimate probability without actually implementing the decision? I'm sorry, Achut, I'm not sure. I'm sure that I'm not pronouncing your name correctly. So the question is, how do I estimate, how should we attempt estimating the probability without actually implementing the decision? I don't think you can. I don't think you really need to use some supervised learning. And by supervised learning is that you should have tested the different outcomes so that you can get, so the simplest way to estimate the probability is using the frequencies for each of the possible outcomes. And for that, you need to observe the frequencies. That's the simplest way. And the more advanced methods using supervised machine learning, certainly we need some training data. And for that, we need to have made the decision. And that, I think I'm running out of time, but that actually takes me to a somewhat kind of paradoxical result in Bayesian statistics and Bayesian inference, that if the outcome has never happened, you don't even have a prior for the outcome. So you can come up with a prior, but if one outcome has zero probability, you can't even try to estimate the posterior. So you certainly need to have implemented the decision before. There's another question. Ali, when can we decide to give less weightage on prediction? So I'm not sure what that means, Ali. I think we can discuss this offline because it's either a very deep question that will take us several hours, or I'm misunderstanding it. I see more reactions here, but someone raised their hand, but let me see if I'm missing something. Sorry, I can't see what you're saying unless you write the question on the Q&A tab. Cool. So that's what I wanted to discuss today. Again, this is my approach to data science. I don't think it's super original. Many people are doing it, not most of the people, and we should be trying. In my opinion, data science could move forward way faster if we think of data science as improving our decisions. And in my personal experience, it will certainly help us in our careers, because that's when our stakeholders will find a lot of value in what we do. And just to finish with some shameless self-promotion, this was a high-level talk about many of the topics that I cover in the O'Reilly book. Hopefully, some of you will find it helpful. Great.
Daniel, just to go along with your shameless self-promotion, Femi actually asked another question. Does your book cover causal inference? And do you know of any good, easy to understand and relevant resources for causal inference?
That's a great question. The book is certainly not covering the interesting parts. I give a very brief introduction to causal inference, very, very brief, basically trying to sell why it's important. I can give some offline recommendations because there are some really great books out there, some books that I really love and passionate about. Happy to share them with you, and you can share them elsewhere, Nathan.
Great. And last question that doesn't really have anything to do with the talk, but has everything to do with your book. What bird is on the cover, and why did you choose it?
That's a question that I always get. So O'Reilly always publishes their books with an animal on the front cover, and unfortunately, the authors are not able to decide which animal. I would have posted a picture of my dogs that are here with me, but so I don't really know what bird that is. I was told some time ago, but I don't know. Sorry.
Perfect. All right. Well, thank you, Daniel, and thank you everyone for attending today. Some shameless self-promotion on our end. We do have another couple of webinars happening next week. One of them is titled Finding the Tallest Tree, Comparing Tree-Based Models. And that is with Jared Lander. He's the Chief Data Scientist at Lander Analytics. And he also wrote the book R for Everyone, which is a book we highly recommend at all of our boot camps. And we've actually given away quite a few of those books. And we will also be doing an ebook giveaway for R for Everyone. So I've posted the link in the chat. I'm sure my team has also posted it in the live streams. So please join us next week. And thank you all for coming. Again, Daniel, thank you very much. And everybody, have a great rest of your week.
Thank you, everybody. Bye-bye.
Bye.